So the other part of this extension 2 topic of motion is this idea of further projectile motion. To start off with, I'm going to look at some old extension 1, because it used to be in the extension 1 course. But variations on it, they were a little bit different than a standard projectile motion question. So this one back in 2014 was an interesting one. So we take off, it's a ski jump. It's located at the top of a slope, so there's the slope going down at 45 degrees there. Skier takes off with our velocity and the angle, well, it's an acute angle obviously. Skier lands on the slope at some point P, and we know it's D down the slope. And they've kindly given us the equations for the horizontal and vertical displacement, so we don't have to derive them. First part of the question, a little bit of a gift. Show that the Cartesian equation of the flight is this. Now basically we've got to eliminate the parameter, eliminate t. Now make t equal to x on v cos theta. Substitute that into the y. I need to manipulate it and get it into the form that they want. So playing around with that, I've got sec squared, yep, that's good. Sine on cos is tan, so that looks all good. That matches what they want. Show that d is this expression here. This is a bit more interesting. Well, the way I approach this one, and so I'm going to look at this ratio of y on x. Now y on x is minus a half gt squared plus vt sine theta over vt cos theta. So we think, well, why on earth is he doing this? Well, because we know the tan of minus pi on 4. So just going back to our diagram, if I imagine a right angle triangle there at the point P, then the tan of that angle would be the y value over the x value. That's why I'm using this idea, because it's information I know. Tan of minus pi on 4 is negative 1. So now I can hopefully rewrite this and get what we need. So 2vt cos theta is gt squared minus 2vt sine theta. I've got a quadratic. Well, I've written it slightly different, but t squared is 2vt on g sine theta plus cos theta. Okay, this is good. We've got sine theta plus cos theta in the answer, so maybe we're heading somewhere. So t, I can divide both sides by t, because I know t is not 0. You can't take off and land instantaneously. So I know it's a positive number as well. So I can just divide through by t. So I now know t is that expression. 2v on g sine theta plus cos theta. But the other thing I know, trig work, I can say, well, d is equal to the square root of 2x. If I go back to that right angle triangle, I can work that out. And x was vt cos theta. So if I substitute in the t I just found into that t, I get the expression that they're looking for. So a very different question for projectile motion that particular year. They then want us to differentiate, and this is a hard thing to say, the d, the theta. We're going to the d, the theta. And it's going to be this lovely expression here. Alright, we just showed that d was equal to this. First thing I notice is my answer's got cos 2 theta, and I've only got theta. Clearly I'm going to need double angles in here somewhere. So let's expand. Sine theta cos theta, that's good. I can get a double angle in. Cos squared theta, yeah, I can get a double angle in there maybe. I can certainly turn this first one into a half sine 2 theta. I might just leave the other one as cos squared theta for now. Because when I differentiate the cos squared, I will get 2 cos theta sine theta, which is sine 2 theta. So that gets the other double angle result in there that I'm looking for. So I end up with the result, cos 2 theta minus sine 2 theta. Show that d has a maximum value. Okay, well there's d. Really tempting to use calculus, but I'm not going to. Even though they just got me to differentiate. It might even be what they were expecting. But, watch this. I can rewrite this as a single trig. Because you see, I've got a sine 2 theta plus a cos 2 theta. Auxiliary angle, I can bring that whole sine 2 theta plus cos 2 theta in and make it cos 2 theta minus pi on 4. I've now got a trig that I know something about, because I know that that trig expression will be a maximum when 2 theta minus pi on 4 is equal to 0. Therefore, the whole thing must be a maximum when 2 theta minus pi on 4 is equal to 0. Well, there you go. Must be when theta is pi on 8. So d will be a maximum when theta is pi on 8. Notice it did not say find the maximum value. It just simply said show that it has a maximum value and then find the value of theta. So I didn't actually have to go and find D. Oh, this one here, the dumb bird question. This is a great question. This actually came out of that, I think it was a very old Fitzpatrick textbook, but it's the dumb bird question. A stone is thrown so that it will hit a bird. A bird's sitting at the top of the pole. So you're going to throw a stone at it and you want to hit the bird. However, as soon as I throw the bird goes, not going to get me, and flies away in a horizontal straight line of speed of 10 metres per second. But as I say, it's a dumb bird. The stone reaches a height of double that of the pole, and then as the stone comes down, it hits the bird anyway. You see, if the bird was smart, it would have flown towards me, not away from me. Okay. Find the horizontal component of the velocity of the stone. Well, assuming there is no air resistance, we know the path of the projectile will be a parabola. And this, again, I'm not going to use calculus. Sometimes your knowledge of the quadratic function can assist in solving projectile motion questions. We know the greatest height will occur at the vertex of the parabola. So I'm going to let the coordinates of the vertex be 0, 2h, double the height of the pole. Thus, I know the equation of my parabola must be y equals 2h minus some constant times x squared. So it's going to have that shape. That's if I centre it like so. So there's the picture of it. Y equals 2h minus x squared. I've drawn h in there. There's the pole. The bird's gone that way. Bang, and we can see the parabola hits the bird. Now we know that when y equals h, h is equal to 2h minus k squared. That's sub in the y value. So kx squared is equal to h. Therefore I get x is plus or minus root h on k. That means that that point there is, the x value is minus root h on k h, and the other point must be plus root h on k h. So the bird flies a total of 2 root h on k metres at 10 metres per second, if it's going to get hit again. Now we know time will be distance over speed. Our classic speed equals distance over time rewritten. Subbing in the distance over the speed, I get that the time is 1/5 root h on k. Now when y equals 0, then 0 is equal to 2h minus kx squared. Solving that, I get that x is plus or minus root 2h on k. That point there must be minus root 2h on k. So the rock will travel root 2h on k plus another root h on k. Root h on k times root 2 plus 1 metres horizontally. Now speed equals distance over time. So subbing in that, I now have the speed of the rock. So the horizontal velocity of the rock or stone is 5 root 2 plus 1 metres per second. I've solved the projectile motion question, did not use one bit of calculus to do it. Everything was done just on my knowledge of quadratics. Dumb bird. Should have explained towards me, wouldn't have got it. Alright, well let's now have a look at this new Extension 2 course. It specifically mentions projectile motion and resistance, and in the entirety of the HSC there's only ever been one question. And that was in 2003 in the old syllabus. Question 5b it was. And here it is. Particle of mass m, thrown from the top of a very tall building, initial velocity, standard sort of stuff. But it experiences a resistance proportional to its velocity in both directions. Thus, our equation of motion, they gave them to us, so in the horizontal direction it'll be minus k times the velocity, and in the y direction it'll also be minus k times the velocity, but minus g as well. K is a constant, and so on. Make sure you always pay attention to these sort of lines. You are not required to show these. They're giving it to you to save your time. Derive this result. So the expression for the horizontal velocity. Okay. Well, they told me that acceleration, I'm using d to t, is minus k times the velocity. So t is minus 1 on k. The initial velocity was u cos alpha. Subbing into this log. Now, that's t in terms of x dot. We want x dot in terms of t. So playing around with that, we eventually get the expression that they want. Okay. This is where possibly I made a mistake. Because it says verify, not derive. And I stupidly derived it. Maybe took more time. Verify just means, well, show it works. I could have just differentiated and showed that it works. But no, let's do it the hard way. Okay, y to t, or d dot y to t. Woohoo. Okay, same as I did in the last one. Okay, integrate, sub in, rearrange. Eventually, we get the expression that they want. So I went and derived the whole thing. Well, it still answers the question, just maybe took me a bit longer than it could have if I just simply verified that it worked. Find the value of t when the particle reaches its maximum height. Well, maximum height occurs when vertical velocity is 0. So t equals that. I guess the advantage of making that mistake is I already have my expression for t. If I verified, I wouldn't have had it. So what do they call that? Serendipity. Discovery by accident. Okay. Subbing in, and I get it very quickly. So maybe it was good that I did it the wrong way in the last part. What is the limiting value of the horizontal displacement of the particle? The limiting value of the horizontal displacement. Well, remember, we've found a velocity equation. Velocity is dx to t. Again, but we want the limit as t approaches infinity, the limiting value. U is a constant, cos alpha is a constant. I'm essentially just integrating e to the minus kt, which is a nice easy integral. So going from t to 0, well, we've got our backwards exponential. As t approaches infinity, we know that goes to 0. So there it is, u cos alpha on k. So as I say, that was the only one that had ever appeared with projectile motion and resistance. The new course comes along, and they came up with this in 2021. Still didn't have any resistance in it, but anyway, projectile motion, let's do it. A particle projected from the origin, initial speed u, angle of theta, usual sort of stuff. Everything's the standard, basic extension 1 version of a projectile. Okay, we're using vectors, but that's extension 1 as well. No different. And in fact, they've given us the position vector. Do not prove this. So there it is. Horizontal ut cos theta, y direction minus gt squared on 2 plus ut. Everything we're expecting to see. For some values of theta, there will be 2 times during the flight when the particle's position vector is perpendicular to its velocity vector. Find those values of theta justifying that both times actually occur during the time of flight. Let's see how we go. There's the displacement vector. Well, obviously I'm going to need the velocity vector here. So, differentiate, and we get u cos theta and minus gt plus u sin theta. But they've said they are perpendicular to each other. Well, that implies that their dot product is equal to 0, which allows me to come up with an equation. And here it is in all its glory, which can be simplified down to be this. U squared t plus a half g squared t cubed minus 3 on 2, there it is, gut squared, sine theta equals 0. But we know t is greater than 0 because this is happening during the time of flight. So t is, we're talking about a positive quantity here, which therefore means I can divide everything by t, and it's not an issue because I'm not dividing by 0. But the other thing I've done there, you'll notice I've got rid of the fractions and multiplied everything by 2 as well. So we have g squared t squared minus 3 gut sine theta plus 2u squared is equal to 0. Remember what we're trying to do? We're trying to find 2 times of flight. Now, if there are 2 times that it happens, then I know the discriminant of that equation must be positive. Okay. We now find the discriminant. So 9g squared u squared sine squared minus 8g squared u squared must be greater than 0, which leads me to sine squared has to be greater than 8 on 9. Therefore, sine squared goes in between 8 on 9 and 1, because it can't be bigger than 1. And theta, remember, is an acute angle. So there's my boundary for sine squared. Got to go between 8 on 9 and 1, which means the square root of 8 on 9 is less than sine theta. I think I got 90 in there too early, haven't I? That should be less than 1, not less than 90 degrees. But then 90 comes into it, because we can say, well, all right, we can find the inverse sine of this. Now, inverse sine is a continually increasing function, so I can apply it to my inequation and the inequalities are preserved. So it's true that the inverse sine of 2 root 2 on 3 is less than theta, is less than 90 degrees, and to the nearest degree, the inverse sine of 2 root 2 on 3 is 71 degrees. So I now know that theta has to be between 71 degrees and 90 degrees. Okay, but going back to our question, we have to justify that it happens during the time of flight. So what is the time of flight? Well, it hits the ground when y equals 0. Okay, back to this equation then, our y equation, and we can get an expression for the time when it hits the ground. 2u sine theta on g. So both values of theta have to occur when t is in between 0 and 2u sine theta on g. Got to happen during the time of flight. Okay, let's go back to our gut equation. So g squared t squared minus 3 gut sine theta plus 2u squared equals 0. So solving for t, we get 3gu sine theta plus or minus this wonderful expression, which is very messy. So I'm going to change it to this. 9 sine squared theta minus 8. How on earth did he do that? Yeah, just divide everything by g. Oh, and u squared. So I factorised the u squared outside of the surd, you'll notice as well. So now that surd there, that 9 sine squared theta minus 8, is a little bit neater. But hang on a sec. 3u sine theta minus u root 9 sine squared theta minus 8 must be bigger than 3u sine theta minus u square root of 9 sine squared theta. No, the one on the left's got to be a bigger expression than the one on the right, because right, you're going minus this. So 9 squared minus theta is smaller than that. We're taking it away. Bang! Well, hang on. That's equal to 0. So I now know that this expression, 3u sine theta minus u root 9 sine squared theta minus 8, is bigger than 0. So both of the times are indeed positive. Well, which one's the larger value? Well, the larger value must be the one that goes 3u sine theta plus u root 9 sine squared theta minus 8 over 2g. And that has got to be less than this expression, right? Because sine squared theta is less than or equal to 1. The biggest 8 sine squared theta could be is 8. So therefore this expression underneath here must be less than the one on top. Okay, so we now know that t has to be less than 3u sine theta plus u sine theta over 2g, which is 2u sine theta over g. Well, if that's the bigger of the two times, well, then the other time must also occur during the time of flight, because the biggest one is 2u sine theta on g, and that occurred in the time of flight. Well, we said the time of flight was somewhere back here somewhere. There it is, tu sine theta on g. So therefore, theta must be in between 71 degrees and 90 degrees. What a great question. 6G.